Okay, in this segment I want to look at how recursion and pattern matching can work together to give us some elegant and different approaches to solving problems. So let's look again at Fibonacci. Again, I shouldn't apologise for this. It's a simple case, but it does illustrate a whole lot of the things that we'll meet when we do more complicated recursions. We can write a direct recursion that very clearly describes the Fibonacci sequence. First number is 0, second number is 1, and the remainder are got by adding pairs of the previous two. So that's our direct recursion. We had a much more efficient solution that was based on using accumulating parameters to hold the previous and current values. And what we did was count down, and at each time we counted down, we made the current the new previous, and the previous plus current the new current. And if we count down the appropriate number of times, we get the Fibonacci numbers coming in those accumulating parameters. But let's see if we can do it a different way. Can we do a direct definition that will have the same efficiency as our tail recursion, but will be a more directly defining the Fibonacci sequence? Well, let's not define the result of our function to be a single number, but let's define adjacent pairs of Fibonacci numbers. So we'll say fib p of 0 gives the pair 0 and 1, so the first two Fibonacci numbers. What about in the general case? What do we do? Well, what we want to do is take fib p of n minus 1, and that will give us the previous and current values, and we recombine those to give the current and previous plus current. So what that's doing is, because we have access to two numbers, we can then generate the next two without having to do a duplicated recursive call. And you can see that. So what we're getting here is a combination of what we did with our two accumulating parameters, but we're making them the result rather than doing the accumulation in the parameters. So we have a result that's more complex, and then we get our Fibonacci number by selecting the first of the fib pn pair. And we do that by a pattern match. And you can see in here what I've done is I've used a pattern match inside the body of these functions to extract the components from something that we know is a pair. And this is one of the uses of pattern matching. It allows us to extract components from complex data structures. And we're using it twice here, once inside the body of fib p of n and once inside the body of fib of n. And in both times we know that the thing on the right hand side is a pair, so what we're doing is saying, in the first case we want both components, in the case of fib of n we just want the first component. So the second field in our left hand side is a wildcard. So we're using pattern matching here to take apart a complex value. And also, of course, in the two clauses, we're using it to distinguish between different cases. So pattern matching for distinguishing between cases and for pulling complex values apart. Okay, now I did say when we talked about representing data how we use tuples to represent more complex objects. And here let's just talk about a case of representing geometric objects. We have a circle here which has a centre xy and a radius r. We have a rectangle which has a centre xy, and we're assuming the sides are parallel to the axes. It has a height h and a width w. In both cases xy is the centre of the object. So we're representing these things by tuples. We're using the first field of the tuple to hold an atom, which tells us what sort of data we've got. And then we can define a function over these that returns the area. So if we get a circle, the result is math pi r squared. So we get pi from the math module, and we square the radius. In the case of a rectangle, we multiply the height and the width. Now, you can see here that we are using pattern matching to do two things. We are distinguishing between the two cases, and in each case we're using pattern matching to extract components. And I just wanted to conclude by making that conclusion. Pattern matching does these two things, and we get the power of pattern matching when we use it to do both distinguishing between cases and extracting data in each case. So we can distinguish between different kinds of data, and within a single kind of data we are able to extract components. And taking those together gives us a very nice way of expressing quite succinctly what it is we want to do. Much more readable than having to define explicit selectors and so on. So that's it. Putting pattern matching together with recursion allows us to get our direct recursion, which is an efficient Fibonacci, and we're seeing that pattern matching is usable both in definitions of functions, but within those definitions to extract components from results, for example. And that's it for this section.